Okay, so I present a talk about spin Hall effect. So this is the simplest way to present the spin Hall effect. There is no ferromagnetic layer here in this story in the first step. And here, so we have this picture in which, okay, this is a conducting layer schematized here. And what we can see is that the Hall effect and the spin Hall effect is, in fact, very, very similar. And we operate on the same object, which is a thin layer, non-ferromagnetic. This can be discussed later. And in contact with the electric generator here. And furthermore, just to simplify the description, it is, we assume the invariance by translation along the x direction. So we ignore what is going on in the contacts here and here, which is complicated. And we assume the symmetry of the two edges before the application of a magnetic field. And we assume that there is no hole. The structure is simply connected. He and she here is not a problem of gender balance. It's something else. Okay, but just, if you apply a magnetic field, a static magnetic field, of course, we have the Hall effect. Everybody here knows very well what is the Hall effect with the generator here. What is going on is that we have accumulation of electric charges at the edges. And due to the accumulation of electric charges, we can measure the Hall voltage. Here, in the case of the spin Hall effect, there is no need of applying an external magnetic field. And what we observe is the accumulation of spins at the edges. And in fact, there is indeed an effective magnetic field in the structure, which is the spin orbit magnetic field. And that's why we need here a strong spin orbit material. And there is no voltage, transverse voltage, if the structure is symmetric, if the edges are symmetric. Okay, I suppose you know that very well. And the goal here is to find the distribution of electric charges and spins across the whole bar. And maybe you can ask, oh, well, it seems to be very basic, very simple. I think it is not trivial because we are out of equilibrium. This is a non-equilibrium stationary state, and what is going on is that the electric charges here, the spins here are moving. There is a current, and we want to know what is the distribution of the currents too. And to do that, first I will present the result. In fact, an illustration of the result of the study, and that I will describe in the next slides. And the result is illustrated here. This is the usual Hall effect, illustrated by the currents, the surface currents flowing at the edges. And if I say at the edges, it means precisely in this volume, which is the Debye Fermi length scale, the length at which the electric charges are accumulated. And here, okay, we have a strong current injected by the generator here. And if we subtract the total current, which is here, we subtract this constant current, we define the surface current, and this is with opposite directions here, depending on the sign of the carriers, of course. In the case of the spin Hall effect, we have, of course, the same thing. This is totally analogous. And what we have is also the surface current. And in that case, the surface current is a pure spin current. There is no charge current. There is only spin current here and here. And if we have also spin flip scattering in the system, this is usually the case, then we have, of course, this pure spin current which is flowing across the sample, which is well known. And the question is, how can I show that? How can I demonstrate this rather simple result, but not easy to demonstrate in the case of the spin Hall effect? And the way to show that is to use non-Ecole thermodynamics. And okay, here is the big important works about non-Ecole thermodynamics. This formalism is well defined. And I just recall here a nice quotation, nice citation of Gibbs here about the choice of the formalism we use to describe something. Of course, the choice of the formalism is the greatest simplicity. And just I add something maybe for the discussion. It is probably not a good idea to start with non-Hamiltonian if you want to describe something generic, especially transport effect, because it's generic and Hamiltonian is usually very specific. Okay, just for the discussion if we want. Here is the overview of the talk. Now we know the objective. And the way to do that, first I want to show something which is rather easy to describe is the role of screening in the Hall effect, in the usual Hall effect. And this is the Corbino disk. And the objective too here is to introduce, the current and to demonstrate the presence of the longitudinal currents in the case of usual Hall effect, and then to generalize that to spin Hall effect with the definition of the two-spin channel, and I will end with that. And another last objective here, which is also maybe for the discussion, is about how to define the efficiency of charge to spin current conversion. Okay, about this story, this is a picture about the usual Hall effect. So I didn't put the generator on just to simplify. And here, this is a charge accumulation. And the question is, why does the system Hall bar accumulate electric charges? The answer is, and this is a way to describe the least power dissipation principle, the answer is to say the system wants to kill the transverse current, the current which is going here. And then this is easy to prove experimentally here, of course. It suffices to contact the two edges here and to have the perfect contact, to short circuit. And the way to do that perfectly is to take this edge, to turn here, and to stick the edge to the other. Then you are sure that it is impossible for the system to accumulate electric charges. So this is the shortcut, and what we have is the Corbino disk. So the Corbino disk, you have this electrode is the internal electrode here, circular electrode, and this one is the external concentric electrode. The generator is here. Okay, here what is important is the current is not modified when you apply the magnetic field in the Hall effect. Because, this is because the system kills the transverse current, and instead we have an electric field with this Hall angle here. And in that case of a Corbino disk, this is the opposite, but we have the same Hall angle, so for the same equivalent system. But now the Hall angle is defined by a switch of the current lines, and the electric field is maintained here. Radial is not changed because there is no accumulation of electric charges. This is the same electric field. This is why we have something important here. We go from galvanostatic condition to potentiostatic condition. But at the time of Orso-Corbino, the question was if it were the same effect, the Hall effect. So the answer is yes, of course it is, but with different boundary conditions, with different constraints. So, and I answer to a question of Cairo of this morning. This guy is, I think, an important Italian physicist, and not well known. Okay, Corbino. Ah, that's right. Okay, but we have to. Okay. So we have to keep that in mind for the spin Hall effect, which is more complicated, but this picture is very important in this story. So we have here the transverse current, and this is described here in the publication. Okay, what we have here, what is important to point out, and you certainly know that, the property here about the screening effect is not contained in the transport equation. Transport equation is here. Of course, we have to add the fact that the density of carrier is not uniform. So we have a diffusion term. So we recognize here the usual transport equation for semiconductor. And here, this is the whole term. And we just have to add here the gradient of the diffusion term. But otherwise, there is nothing that explains why we have that, so the accumulation, the screening. And the other way to, this is the only way to describe the role of the accumulation of electric charges. There's just the Maxwell equation, Maxwell-Gauss equation, where we create this supplementary electric field transverse due to the accumulation of electric charge. But this is just a consequence. Here, just to be familiar with formalism, I just introduced the few steps here, 3-4 lines that allow the equation, the transport equation, to be derived properly. This is the chemical potential with this dependence to the density of carriers. And here, this is a real pure electric potential. Here we can describe different cases, and we just apply the Ohm's law. That's all. And we can justify why the Ohm's law apply. But okay, here we do not have to use the conductivity, which is not constant in the space, but the mobility constant here, because the space dependence is only in the density. And this is a density mobility tensor, and the tensor can be written that way, just on the basis of the Onsager reciprocity relation. This is very, very general. You can obtain the same thing if you turn your system very fast. For example, you just need an axial vector, or another term, you just need to, okay, I will not go more details for the Onsager reciprocity relations, but then you justify that. And you have the equation. Inserting the chemical potential into the Ohm's law, you have the equation. Okay, just to show that this formalism is useful. Now, what we use is, in fact, the problem, it's also a discussion. As I said, the problem is we have the system accumulate electric charges at the border. But if we want to solve an equation like a transport equation or continuity equation, differential equation, we need boundary conditions. We need local boundary conditions. We do not have the boundary condition because this is the system itself, which is producing the charge accumulation. This is unknown. This is what we are looking for. And that's why this approach is, I think, more efficient. So the approach is to minimize the power, the Joule power. This is written here. And so we just, for the sake of simplicity, we have a reduced power here. And if we minimize the Joule power, of course, we have J equals 0 here, and Joule power equals 0. Of course, this is the definition of the equilibrium. No power dissipation equal equilibrium in thermodynamics. because there is no constraint, we have, of course, to add to formalism the fact that the system is contacted to a generator. We have to add constraints, and the constraints are global, not local. Globally, we have the current is the current imposed by a generator, totally integrated over the whole system, and also the charge conservation is global, is over the whole system. And it is easy to integrate that into in the minimization of the functional. We just have to put here to introduce two Lagrange multipliers in order to take into account the constraints. So this is a well-known technique. And then we have just to derive a functional derivation. And we get the result. The current here, longitudinal current, is proportional to the accumulation of electric charges. And then we can check that, injecting that into the transport equation, we check that we have, okay, the local conservation. This is a consequence of the charges, and we have also an harmonic potential. Okay, this is easy to show. Well, you can say, oh, it's trivial. Of course, the charges are moving, because otherwise, if you are measuring the voltage, whole voltage, we will see the decreasing of your electric charges accumulated due to the internal resistance of your voltmeter. And this is not the case. The whole voltage is very robust. You can measure it even with a very bad voltmeter. And the reason is here, because you have the charges here are permanently renewed. And I think this is something well known, but strangely, I didn't find a description in the literature. Here is a more detailed description, but this is not the point. If you know a publication about that, please tell me the fact that this surface current, which is, evident somehow, should have been described before. But here it's important, the method is important because we can apply to the spin Hall effect. Here, just a slide of introduction with using the paper of Diakonoff and Perel in 71. And here the picture of the spin orbit scattering. And here are the Diakonoff-Perel equation. In our context, phenomenology, the definition of the spin Hall effect is the Diakonoff-Perel equation, the transport equation. So we use, conductivity is defined by, Ohm's law, for example. But this is, I think, very difficult to understand. This is not intuitive. Here we have a nice review of Axel, who, of course, well known. Spin, but the spin Hall effect can be described very intuitively. As I said, it is the Hall effect. It is 2 times the Hall effect if you define that in the framework of the 2-channel model, which is well known and very efficient in giant magnetoresistance. It's easy to describe here the Hall, and oh, sorry, I wanted to show that. This is the spin Hall effect. You imagine that you have an effective field, spin orbit effective field, which is applied in one direction for the spin up channel, conducting channel, and the down direction for the spin down conducting channel. And that's all. If you imagine your system as the superimposition of the 2 subsystems here, you have indeed the spin Hall effect like this. And so you accumulate the electric charges with opposite sign. You have 0. If your symmetry is perfect, you have 0 electric charges, and you have the spin accumulation. This is imposed by the symmetry. The sum is 0. The difference is not 0. And the difference is a spin accumulation. Easy to understand intuitively. But we have also the equation of the transport equation easily. We have here, this is what I have shown for the normal Hall effect in the slide 6. We just have here to put the spin, that's all. We have spin up, spin down, so we put the spin. Well, okay, what we have is the equation here, but we have to take into account the fact that we change the direction of the effective field for the two channels. This is the reason why we have changed the sign here, and that's all. We have this equation. We have to define the spin-dependent electric field with adding here a chemical potential, which is exactly that of the giant magnetoresistance. Nothing different, but in the case we are describing, there is no ferromagnet, there is no spin injection, so we can just remove that for the description here, not for inverse spin Hall effect. Okay, and it's rather, I will go very fast here, but it's rather easy to show that this equation is equivalent to the Diakonov-Peirel equation, but of course, if we project the spin on the z-axis, it's not difficult to generalize to any direction of the spin axis. What is important is that we have the same thing here and here. But there is another generalization here. This is this chemical potential, but I will not use it for this talk. And this is the formalism. We have no 2x2 matrix in order to take into account the spin channels. But okay, this is just the formalism. Now we have the equation, transport equation for spin Hall effect. We just have to apply the principle, minimum power dissipation principle. Now the power, Joule power, is we have just to add the spin dependence with the two channels here and on the chemical potential density here. And that's all. In fact, no, that's not all. Of course, you know that, and this is a big problem. I mean, the difficulty and the specificity of this system is that we have spin-flip scattering. Spin-flip scattering dissipates, but the power is well known also due to 30 years, 20 years of giant magnetoresistance. No, more. And this is the expression used in the giant magnetoresistance. You want to describe the spin-flip scattering, you introduce here this delta mu. This is the spin pumping, or also this is the difference of the chemical potential for the up and down channels. And we introduce here a non-Zager coefficient, which is related to the spin-flip scattering, to the inverse, the square of the inverse of the spin-flip scattering. And we have to add the two global constraints. This is the same as previously. So we have to take care that the constraint is applied on the total current, not by channels, by spin channels. And the same for the conservation of the total charges, not per channel. And there is a very simple case, which is the one at which the spin-flip scattering is negligible, which means that it is the spin-flip scattering length is much larger than the width of the sample. So it's not an absolute value, it's a ratio. The ratio LSF over L should be very big. So you can tune it with the width of your sample. And so now I write the functional, and this is the same as previously without the spin, but we have to take care of the spin up, spin down here, and the derivation is the same, and the result is immediate. And I claim that you can imagine perfectly intuitively what we will have. We have 2 times the Hall effect, so we have the same result with the difference that the current across the sample is 0, like for the Hall effect. This is true for the 2 spin channels. And we have this longitudinal non-homogeneous current, the surface current here, which is proportional to the density of charge accumulated at the edges. So here we have something which is rather unusual, but simple and perfectly intuitive. If you accept the situation in the case of the simple Hall effect, we have to accept that if the spin-flip scattering is small enough. And then we can calculate exactly the density of spin. We can have a quantitative result. So there is not this problem of differential equation and we do not have the local density. But here what is important is that we have something linear. The density of spin is linear. This is not the exponential or hyperbolic sinus. Density is decreasing linearly across the sample, going through 0 in the middle of the sample. Okay, I don't know the time I have, but okay, I will finish with that. Now, what is much more problematic is to do the calculation properly in the case of arbitrary spin flip scattering. But we can do that with a strong spin flip scattering limit. We have also something rather simple with analytical results. And if we do it, we have the results that the current across the sample, so perpendicular current is not 0, and this has this form, and here you recognize the Corbino result is here. We have like something rather close to the Corbino disk in that case, due to the spin flip at the edges. So strong spin flip means local spin flip at the edges, and the charge current is 0. So this is a pure spin current. This is more or less the usual result, well known, but we have here a prefactor which depends on the spin flip scattering length, which is the ponderation, which is described here. So here what we described is this transverse current, pure spin current, and we have furthermore this longitudinal currents, which are the arrows here and here. This is the current, pure spin current, a current of spins, no charge here, no electric charges at the edges. Yeah, there is something to discuss here, but this is the spin current at the edges. And we are here as a function, so of this ratio, width of the sample versus spin flip diffusion length. And okay, here the result when you solve the profile for the charge accumulation, what you will see here, it is the resolution of the Poisson law. What we have here is a well-known result with this part of exponential, with the typical length here, which is described here. But we have here still the solution obtained with small spin flip scattering. And this is important because if we put numbers inside, we obtain linear dependence, which is reminiscence of what is going on without spin flip scattering. Okay, and I finished with that, just pointing out that we have here, for example, this paper of the group of the Polytechnique di Milano with a density of spin here, which is linear across the sample. But it is not systematically observed. So this is in relation with what we have seen this morning also. And I finished with that, summarizing, okay. So just summarizing what I said, stationary state. All I have described is, of course, the stationary state. My definition of a stationary state is the minimum of power dissipated in a sample. We have here the expression without spin flip scattering. This is a linear profile of the accumulation of spins, which is expected. And if we have the spin flip scattering, we expect also a part of the solution is this linear term, and we have the usual exponential here. And there is some open questions, but I finished. Thank you for your attention.
Thank you. Thank you very much.